to get started. It is our pleasure to have Sekula from South Methodist University. He is a member of the Atlas collaboration. He's the co-convener of the VJet Trigger signature group. He previously worked at Babar as well. His research focuses on heavy quark physics, Higgs physics, and he is also a recipient of numerous awards in both research and teaching, and heavily involved with public outreach. Today he's going to tell us about the current status of the future of Higgs.
Yeah, thank you very much. I kept the abstract intentionally vague because, to be quite frank, until about 3 or 4 days ago, I wasn't completely sure what I wanted to present, but it sort of crystallized for me, especially given the things that we're working on at SMU with our partners in Atlas these days. And so the talk today is going to make this a bit more explicit at the beginning. I'm going to utilize the Higgs decay to bottom quarks as not only to talk a little bit about observing something that was fundamentally predicted to be true about the Higgs, which turned out to be true, but also to motivate a little bit how one can then utilize this as a tool for doing what I think are ultimately more interesting things. You know, as Bo said, I came from the B physics community. I have lived both of the lives of being that precision physicist that spends 9 months measuring a single systematic error for the pure satisfaction of getting it right. And I've also been that discovery-oriented physicist who is really tired of making measurements and just wants to go to look for something, whether it may exist or not in reality. And so I want to mix a little bit of those things together today. You're going to see parts of my talk where I focus on the difficult challenge that LHC experiments, including both Atlas and CMS, are facing when it comes to making more and more precise measurements of the Higgs boson, but also using things that are statistics limited, because we don't know whether or not they exist, or if we know they exist, they're very rare, and we would really like to see them. I'm going to mix all of that together today in a hopefully semi-coherent seminar. So, to review a little bit the motivation for, at least for myself as well as for the whole field, as to why we're on this journey, this many thousands of person journey with this massive instrument in Switzerland, I wanted to start by talking about our little broken universe first, because the fact that the universe has something fundamentally broken in it is what makes all of it very interesting to begin with, not just for physicists, but for everything. Right? So, I teach a lot of undergraduate courses. This is a chance to reflect on the history of science a little bit, whether it's cherry-picked or not. Sometimes you can assemble a very good narrative without really understanding why people thought what they thought at the time that they thought it. We were talking about this a little bit over lunch today. You know, how did Heisenberg write that fundamental paper, getting to the matrix mechanics derivation of quantum mechanics? Where did Schrodinger really come up with the wave equation? What was the inspiration for that? I think it helps to start from observations and theories in order to motivate the next great intellectual leap, because I think we need one. And I've talked to some other people here at the Institute today who are working on those leaps, and I find this all very exciting. So I think it's useful to dig back to the period around the 40s, 50s, 60s, 70s or so in the 1900s and think about what people knew, what they were confident they knew, what they wished they knew, and in no particular, the order I'm telling the story is not necessarily the order in which it happened, but I think it's useful for understanding things, right? So we had all these amazing observations going back hundreds of years, right? Electric and magnetic forces, the establishment of the atom is a real thing, the understanding of its quantized atomic spectrum, prediction of its other properties, the observation of the electron, the observation of the atomic nucleus. And all of this required explanatory frameworks, right? So digging back into the 1800s, you have Maxwell's equations. In the early 1900s, you have special relativity as sort of the theory of all motions, general relativity being the true theory of all motions, and quantum mechanics. And then what results out of this is the relativistic quantum mechanics, the Dirac equation in the 1920s. It cements the massless photon as the carrier of the electromagnetic interaction, but it reimagines interactions in a much more complex theoretical framework, and really gives ridiculously accurate prediction of atomic properties and other things, right? But then we also know that this story ended with a lot of problems. So as one digs experimentally into the nucleus, one is confronted with the problem of both its significant level of stability, given how tightly packed all those protons are in proximity to each other, but also the reality of its instability, radioactive decay and things like that, the overall short range of nuclear phenomena. These pose interesting challenges to a community of scientists that want to explain them. So of course, yeah, you have explanatory frameworks, you have relativistic quantum mechanics, now born out of the previous era. You also have the introduction of new mathematics, including the mathematics of symmetries, gauge symmetries, and things like that. And then you get predictions from this, right? And this caused some problems. So for instance, you could attempt to explain the nucleus using these frameworks, but you very quickly ran into the problem that it appeared that all self-consistent quantum field theories that you would be writing down in the late 1950s going into the early 1960s predicted that you had massless force carriers with infinite range, which just doesn't meet the needs of the nucleus of the atom. And so, this is the situation circa 1960. A lot of people are working on these problems. You have Philip Warren Anderson, who's credited with being the person who really brings the breaking of symmetry into the classical field theory regime in the context of plasmas and the fact that the photon appears to acquire mass under certain conditions in a plasma. The quantum field theory work to understand this problem would be left to Brout, Englert, Higgs, Hagen, Guralnick, and Kibble, who in one fantastic year came up with the full quantum field theory solution to this problem. And of course that problem boils down to this key idea of a spontaneously broken gauge symmetry. So I've illustrated the idea of a spontaneous symmetry breaking here. Books like, I think it's Housen and Martin use the idea of pressing down on a metal knitting needle, and then it will spontaneously, without you being able to predict which way it will bow under enough force. It will spontaneously choose a direction to bow out in, and you can't predict which one in advance it's going to do that, and it breaks the cylindrical symmetry of the knitting needle. Not all of us are playing around with knitting needles. I mean, I did when I was a kid, but that's because I was weird and artsy. Okay? Coffee stirrers that you'll find in any coffee room, typically in any university, the plastic kind, they also have a cylindrical symmetry. And you can spontaneously break that by pressing gently on the ends after gripping it between your thumb and middle finger or something like that. And so I took a couple of pictures of this happening, the spontaneous bowing of random coffee stirrers, to illustrate the idea that the symmetry can break spontaneously, but there's an infinite number of equally valid final states of this system that form essentially a circle around the middle of the cylinder after the symmetry breaks. Okay, well that's a hand-waving way of talking about it. Of course, in reality, in quantum field theory, the way that this was accomplished in the 1960s was by writing down an electroweak potential that explicitly exhibits the possibility of spontaneously breaking symmetry. So for instance, the universe might start out here at a point where a field, the Higgs field in this case, has 0 value, but this is not the stable point of the theory. At some point, the universe will find itself in one of these infinite and equally valid minima down here in a circle around that 0 point of the field. And so the symmetry is spontaneously broken in the vacuum, and this allows you to have things like the force-carrying particles, the gauge bosons like the W and the Z can acquire a mass. And this is extremely useful because this helped us to understand especially the short range of the weak nuclear forces. The short range of the strong nuclear forces has to do more with the particular kind of field theory, non-abelian gauge theory that describes quantum chromodynamics, the theory of the strong force. But this is a key idea that comes out of this era, that this essentially is the right potential to describe this phenomenon. And it's probably the easiest one you can write down. But I think the thing I want to leave all of you with here at the end of today is that this doesn't necessarily have to be the way the universe actually is. And there's a lot of hope in both ATLAS and CMS that we might be on the verge of actually probing more directly the shape of the Higgs potential itself. And I think that's the thing that excites me about all this. And I want to get us to that point by talking about Higgs physics. Okay? So, out of this era, right, we have the prediction, the consequence of all this is that we're forced to postulate the existence of a new particle. It is now called the Higgs particle. It has spin 0, it's a boson, it's integer spin, specifically of 0 internal angular momentum. Since discovering it in 2012, that property has been well confirmed by both ATLAS and CMS. It has other properties as well. Those have also been confirmed. And we're beginning to map more and more its interactions with other particles. In fact, that's how we discovered it. It should have 0 electric charge. That's very well established. That was probably the first thing we really established before we went for the spin and other quantum numbers. The interactions themselves should be proportional to the masses of the particles with which the Higgs is interacting. So for instance, if the Higgs has a direct Feynman diagram, tree level interaction with a particle like a Z boson or a W boson, or a fermion like a bottom quark or a charm quark or a tau lepton, something like that. The pattern, the degree to which the Higgs interacts with those things will end up being proportional to the mass. That's effectively where fundamental mass comes from. You trade the question, where does fundamental mass come from, for the question, what are the pattern of couplings between the Higgs and other fields? That's the question that we're faced with now, and I don't know if that's a more or less satisfying place to be, that we've traded the mass question for a different question. But that certainly is where the Higgs particle has put us. We're pretty confident we know within the context of the standard model where most, not all, fundamental mass comes from. We still don't understand the neutrino. That's a big mystery that cries for an explanation. I'll cycle back to that at the end. But as I'll show you at the end of the talk today, this right here, this proportional to masses thing, is one of the smoking gun signatures for this particle. And of course that then tells us the standard model in this context is highly predictive about the pattern of interactions between the Higgs and other particles, and that will determine how it's produced, how often it's produced, and how it decays and how often it decays, and what it decays into. This is all very well constrained in the standard model. It's predicted to be narrow. It should only have a natural width of about 4 MeV, makes it essentially, for the resolution of direct detection at the LHC, this makes it effectively a zero width particle. It's an extremely narrow resonance. And what's interesting about this is that in the standard model, self-interactions between the Higgs, either through a trilinear or a quartic process, are predicted. And the trilinear and quartic couplings both have about the same strength, 0.13, and that's determined by the square of the Higgs mass divided by 2 times the square of the vacuum expectation value of the field. The problem, of course, was that in the original standard model framing of all this, the mass, mh of this thing, while it appears in all of these properties, was itself not predicted. And while electroweak measurements and fits of those measurements in the context of the standard model over decades would definitely improve the constraint about where to look for the Higgs, still by the time the LHC turned on a decade ago, you have a situation where the mass of the Higgs is only constrained down to several hundreds GeV of range. So you still have to go looking for this thing. It's not that well nailed down. Of course, we did discover it. That culminated in the first announcement of an observation of a new particle in 2012. The next year was spent mapping out some of those basic quantum numbers, spin, charge conjugation, parity quantum numbers. Those all turned up looking like what the Higgs was predicted to look like, and that resulted in a Nobel Prize for some of the theorists who were involved in this idea in the 1960s and 2013. The current efforts, however, are focused on an intense study of this particle, and while it's unfolding faster than I think anybody thought it would, this is still a multi-decadal program, for at least as long as we have a collider to work on. Okay, so I just want to kind of close up this section by contrasting the tales of a familiar force with this force. And this is thanks to my colleague Daniel Stolarski at Carleton. I saw him use this in a couple of seminars once, and I really enjoyed this kind of way of telling the tale. Right, so think about the electric force, the electromagnetic force. As humans, we experience the force itself fairly directly very early on, right? You shuffle your feet across a carpet, you touch a doorknob, and you get a shock. You're experiencing the electric force long before you know that there are electrons and things like that. So, of course, the electron was identified in the late 1800s, and it's the fundamental carrier of negative elementary electric charge, isolated in about 1897 as the identity of cathode rays. And then, of course, out of this, the models of the atom were built and so forth. And this ultimately culminated in, the experiment in theory culminated in quantum electrodynamics. By the mid-1960s, this was essentially fully worked out. This is a full theory of electromagnetism that still to this day stands the test of time as a theory of this force. But of course, the Higgs particle, the Higgs field, is a story told backward. So out of that mathematical and experimental revolution, you are able to write down a functioning quantum field theory that allows for massive force-carrying particles, but at the expense of needing an additional field, the Higgs field, which has a particle manifestation, the Higgs particle. The basic quantum theory of the Higgs mechanism was all fully worked out essentially in the 60s and 70s. okay? With a lot of work that went on after that, but the basic ideas were all there. We, of course, didn't know that the Higgs particle existed. All of this could have been a fantasy. It could have been that this thing doesn't exist and that what looks like the Higgs mechanism, the breaking of spontaneous breaking of symmetry, is manifested by some other cause. And we wouldn't really know whether or not there really was this particle until we discovered it. And that didn't happen until 2012, 2013, depending on when you think we really figured out it was the Higgs. And we still don't know if that underlying structure, the electroweak potential, is the right description underlying this sort of force of nature. We don't have direct experience interacting with this force in a direct way, except in that it manifests as fundamental mass. So we still don't know that this is true. We're very confident that this particle exists, but we still don't know that this underlying part of the theory is correct, and we would really like to know if that's true. And personally, I hope it's not, because then we have an obvious and direct thing that we can probe that would tell us that the standard model is officially broken in the laboratory, and we have an opportunity to figure out what the correct theory of nature ultimately is. All right, so the players of the standard model, right? So you have the 6 quarks, the 6 leptons, the force-carrying particles, and the Higgs. The standard model has a lot of parameters that have to be measured, but they also has a lot of constraints. So once you start picking at those measurements, you can start making predictions of things you haven't yet measured, and that's what makes this such ultimately an extremely powerful model. And of course, the exception had been the Higgs sector. The Higgs particle mass was not well constrained at all. But now that we have it, everything is determined from it in the model. And that means that this part of the standard model really has to live up to extreme scrutiny at this point. So if we think about this process as peeling back the shadow that nature's been casting on our understanding for a long time, in 2011 we were very confident of all of these players in nature. And between 2013 and 2019, we became very confident that the Higgs existed and that it has a very well-defined pattern of decays, and I'm going to focus on one of those today, Higgs to BB bar. But we're still not completely confident that this underlying electroweak vacuum structure is the right description. We don't know that this really is the structure of the vacuum in the electroweak theory, and we would like to know that. So this is still shrouded in mystery, and we'd like to peel that veil back a little bit more, and I'll talk a little bit about how we can do that. All right, so let's sort of take stock of what we want to know and what we think we know about the Higgs, especially as regards particle decay. So the Higgs can decay into many things. I've put a bunch of the prevalent things it can decay into here. And just to give you a sense of scale, the standard model for a Higgs of mass 125 GeV predicts that Higgs to BB bar, a bottom quark and an anti-bottom quark, occurs 60% of the time. And yet, we only discovered this process last year because looking for a Higgs decaying to a pair of QCD hadronized jets in a hadron collider is an insane task and required a lot more time than the discovery, which was done on different decays of the Higgs. One of those was Higgs to W plus W minus. That's about 22% of the branching fraction of the Higgs. Another discovery mode was Higgs to ZZ star and Higgs to gamma gamma. Now, Higgs to ZZ star by itself is 2%. Higgs to gamma gamma is 0.2%. But you have to fold into this the things you can actually detect in the final state with good efficiency. So once you take that into account, you're down to about 0.1% for Higgs to ZZ star to things you can easily see with either the CMS or the Atlas detector. So we discovered the Higgs on some of its rarest decay modes and one of its more prevalent ones, Higgs to WW. Higgs to tau tau, the first of the fermionic final states, was the next sort of domino to fall in all of this, sort of near the end of run 1 and very confidently at the beginning of run 2, which started in 2015. And Higgs to BB bar is the latest of these to be discovered by both Atlas and CMS, and that was last year, using only about half the data set. And I'll talk about the challenges in moving that forward as part of this talk. Okay? So I'm going to focus for the rest of the seminar on Higgs to BB bar as not only an opportunity to make a measurement of something that was definitively predicted by the standard model, but also as an opportunity to study other things that the standard model predicts, but maybe more on the edge of its ability to do so. All right, now the second act here is just to remind you a little bit about the Large Hadron Collider and the Atlas detector. This won't take too much time, but this will be an opportunity for me to talk a little bit about some of the work that Mo mentioned that we do at SMU, which has to do with software triggers, and specifically software triggers designed to identify bottom quark-initiated jets. So the reason this is ironically entitled "We Encourage No Big Searches" stems back to one of my favorite hindsight quotes from a theory paper in the history of the last 50 years. And this comes from Ellis, Gaillard, and Anopoulos. And it's, we should perhaps finish with an apology and a caution. We apologize to experimentalists for having no idea what is the mass of the Higgs boson. For these reasons, we do not want to encourage big experimental searches for the Higgs boson. But we do feel that people performing experiments vulnerable to the Higgs boson, I love that phrase, should know how it may turn out. So basically, this is a field guide. You know, this is a rare thing you're looking for. Don't go out into the world only spending money to look for this. But if you're doing other things, here's what it might look like if you spot it. Now, of course, we did do massive searches, right? Starting after the successes of UA1 and UA2, the US and Europe launched programs to in part, ultimately hunt down the Higgs boson. The Tevatron in the US, the Superconducting Super Collider, and the Large Hadron Collider in Europe. And it culminated successfully, but I think not perhaps the way everybody back in the late 70s and early 80s thought it was going to. Nonetheless, I really love this. We do not encourage big experimental searches. Well, joke's on them. We did it anyway. Right? So this is our big experimental search. This is a schematic of the Large Hadron Collider. We're facing south. This is the France-Switzerland border. France on the right, Switzerland on the left. The city of Geneva is over here. Okay, there's Lake Geneva. CERN is located right on the border between France and Switzerland, and the ATLAS experiment is conveniently located not a 10-minute walk from the SMU office in Building 1 at the CERN laboratory. Our friends at CMS have a bit more work to get to across the ring to their experimental site. But both sites are roughly about 100 to 150 meters under the ground. That's where the tunnel is actually located. This used to be the Lhc Tunnel, and it's now the Lhc Tunnel. And currently the LHC operates at a center of mass energy of 13 TeV at 6.5 trillion electron volts of kinetic energy per beam. 2,800 bunches of protons circulating in the ring. Each has 100 billion protons. That has consequences. And the bunches cross each other every 25 nanoseconds. And as you'll see, because we want high intensity running, the price we pay for this is that you don't only get one proton-proton interaction per bunch crossing. We actually suffer about, on average, 35 to 40 on average. It can go as high as 75 or 80 per bunch crossing. And that's only going to go up and get worse as time goes on, as the LHC continues to push this machine forward, which they have been doing very nicely and very aggressively. Okay, so fundamentally the Large Hadron Collider is really a gluon collider in a Higgs factory. And this cartoon sort of illustrates what's going on here. So you're hurling protons at each other at some ridiculous fraction of the speed of light. There's at least 6 nines after the first decimal place in 99.9 something, and then you get to the non-9 number. At these energies, the protons mostly look like bags of glue to each other. And so most of what happens is that the gluons in each of the protons will interact, and that if you get a really nice high transverse momentum hard interaction, you can produce new massive particles. And one of those was the Higgs boson. The gluons are really abundant, they interact readily, they really define most of the interactions of these things. And because the Higgs is most likely to interact with heavy things, not gluons, the leading process for producing this via gluon interactions is actually a loop process. So you'll have 2 gluons come in, they'll split into top or bottom quarks, which will fuse and then annihilate into the Higgs. So the Higgs readily should interact with top and bottom. They're the heaviest particles in the Standard Model, heaviest and second heaviest, that are fermions. And so this coupling should be rather large. And so this turns out to be the primary way, and I'll show numbers later, that we make the Higgs particle. Okay, so but we rely on this loop process as the dominant production mechanism for this. And just as a hand-waving thing, the LHC at sort of the most recent operating conditions makes about 1 Higgs particle every few seconds. So we have many millions of Higgs in principle that are being produced, but that's not how many we're able to record to disk. That comes at a price in triggers. Now, of course, that cartoon I showed you is really just that. It's a cartoon. This is a more realistic interpretation of 2 protons interacting. But even then, this is a program called NCViz that will take a Pythia simulation file and visualize it for you as the sort of time-ordered graph of all the processes. This is the proton-proton interaction producing a pair of top quarks. So there's a top and there's an anti-top in red and blue. The rest of this is all gluons and gluon interactions, and then finally hadronization, and then energy clusters that would ultimately strike your detector. So this is sort of where the theory part of the simulation ends, and then it would be handed over to a detector simulation like GEONT 4. But even still, this is only one proton-proton interaction, right? That's not what's going on in the LHC. This shows you the total over the 4 years of running for run 2, the total mean distribution of the number of interactions per bunch crossing in the LHC. And you can see that the mean is 34.2. Okay, we went as high as a mean of almost 38 in 2017. But we had numbers of proton-proton interactions that exceeded 70. And I'll show you a plot in a minute that reveals that in the data. Okay? So this is a massive challenge, because that means that for every one so-called hard interaction that might result in something we're interested in, there could be 33 other soft interactions that put a bunch of jets into the same experiment and paint the detector in energy that we're going to have to subtract off if we want to see the hard interaction, the interesting one. And to give a picture of the data taking over run 2, things started out rather slow in 2015. We only took a little data, then things cranked up in 2016, and then again in 2017, and then again in 2018. So again, it's been really delightful to work on the LHC, although every year it's a new challenge to people like me who work on the trigger system to make sure that data doesn't fall on the floor because of the sheer rate of data taking that we're confronted with every time the LHC says, ooh, we found a new way to increase the luminosity. Great. That doesn't mean we necessarily found a way to run our software faster. All right, and I'm a software person, so I'm constantly worried about how much CPU time an algorithm takes to execute and how many of those executions we're going to be able to get before the millisecond window for making a decision at the trigger level kills the data taking and we lose the event. All right, so the total, in inverse femtobarns, the total physics for Atlas, the total data that's good for Atlas for doing physics analysis is about 139 inverse femtobarns. The LHC delivered 156 inverse femtobarns, and recorded was 147. So the gap between recorded and physics is in principle recoverable with additional data quality measures. It depends on how bad a data quality problem we had during that period. But in principle, some of that is recoverable, and that number may go up from 139 closer to 147 as time goes on. That's a game we can play. Oh, yeah.
What do you mean by root for physics?
This is the stuff that, so for instance, just to give an extreme example, if there was some data taking issue that inhibited readout of the calorimeter for the first hour of a run, that data might not be considered good for physics because you now have a hole in your calorimeter, and that's going to mess up your missing energy calculation. There may be some physics you can do with that data, but not generally speaking, all physics analyses might be able to use that. Another example that will alter good for physics is whether a suite of triggers that your analysis needed was actually running at the time. High luminosity data taking conditions, sometimes we throttle those triggers. Then when the luminosity drops after 6 hours, we turn those triggers on. So that limits the amount of luminosity you might get. This is a general statement for the whole collaboration, but there are case-by-case things that change that as well. But generally speaking, if part of your detector is not operable, it's risky to use that for data analysis because you may not be able to control for that effect. Okay. This is a schematic of the Atlas detector, 44 meters long, 25 meters high. There are some cartoon people for illustration. If you ever get a chance to visit this, CMS I think is a much more visually stunning detector. Please, is this being recorded? Please don't tell my colleagues on Atlas that I said that. When you get up close to Atlas, you really only get to see about that right there. You would walk into a hall from this side, you may be able to see about that. So you'll see part of the muon system, the paddles on the end, and maybe one of these toroids here on the end. You'll be able to see some of the large barrel toroids kind of hiding behind things, but you don't get to see very much of the Atlas detector if you go and visit it. It consists of an inner tracking system for detecting the presence of electrically charged particles and measuring their momenta, an electromagnetic calorimeter system, and a hadronic calorimeter system, and then the outermost part of this volume, good half of the volume or so, is muon detection systems, because the muons will minimum ionize and punch all the way through Atlas. So we sample them before they leave the cavern, effectively. Not much else besides muons can punch out that far in Atlas. They have to make it through our electromagnetic and hadronic calorimeters to get that far out, and they're very dense systems. Okay, So this is just to give you a sense of what you might see. This still is more than what you would see if you visited Atlas, because this is still during the construction phase of Atlas. This is the end cap calorimeter being inserted into the barrel region, but all of this exposed stuff you wouldn't see now. It's much more covered up on this one. All right, so I wanted to talk a little bit about the work that I personally am involved in. So I'm one of the co-conveners of one of the trigger signature groups. There are about a half a dozen of these groups, each tasked with maintaining a different signature. Ours is bottom quark initiated jets. So there's a menu of triggers that involve one or more bottom quark initiated jet signature that one looks for. So what does a bottom quark initiated jet look like? Why is it distinct from other kinds of jets? Most of what the LHC produces are gluon and light quark jets. And what distinguishes them from B quark initiated jets is that the hadronic states that Bs can form when they dress up with light quarks tend to live about a picosecond before they decay. Whereas the light states from gluon or up or down initiated jets, they tend to decay very promptly. So the distinct signature of a so-called heavy flavored jet, one that has a B or a charm quark in it, is that you'll see the primary vertex here where all the jets originate from the proton-proton collision. And then if you look out in radially or along the z-axis in this picture, you want to look for evidence of places where a bunch of tracks suddenly appear out of nowhere, displaced from the primary interaction point. It's a little hard to see here given the color contrast in this image, but one of those potential secondary vertices is here. And that can be indicative of a B quark that was produced here, dressed up in a light quark that travels as a hadron before it decays weakly, and then it decays into a bunch of charged particles and neutral particles. Now that can also result in a charm meson being produced. That's a large fraction of what bottom quarks decay to. Charm mesons also live a long time, so you could get a tertiary vertex in here as well. This sequencing in space, which is also sequencing in time, of this event information is more distinctive for heavy flavored induced jets. And so we have algorithms that are implemented both in the offline reconstruction world and online in the software trigger that can rapidly identify the presence of this kind of jet. I don't expect you to read this. I just expect to motivate the fact that one of the challenges that we face as B-jet triggers is we touch just about every part of the detector, and that's risky for a trigger group. A trigger group is best served by using as little information as possible to make a decision as quickly as possible. We need to make a decision quickly, just like everybody else, but in order to see displaced vertex positions in space, you need tracks. Tracking is not run by default in the software trigger unless you really need it, and we really need it. So we get our jets from the jet signature group. Those are calorimeter only jets. We then take those jets, each of them represents a region of interest in the detector. We look to see where they overlap and we combine them into super regions of interest. This is all to save time later. We then run tracking, but only in those super regions of interest, only in the spaces in Z and in angular space around those jets. That then gives us access to the ability to build the primary vertex in the event and then look for secondary vertices. And we can calibrate the jets using the full offline calibration, which improves our jet transverse momentum resolution, which is a nice benefit of this. We can do vertex finding, and finally we can take all of that information and we can push it into the boosted decision tree. Now the deep learning algorithm that we have, we'll be using that in run 3, to make a decision, is this jet B-like or not? This is a very long sequence of algorithms that we have long been relied on to maintain. That's been taxing on a group that's small. We only have about 12 people in our group doing this. The good news is that we're in the process of upgrading the Atlas software to massively parallelize it, and that has resulted in some reshuffling of where things get executed. So in the future, we're going to be more able to focus on things like the vertexing and the final flavor tagging stuff, and less on all this other jet-related stuff, getting the tracks and then doing the calibrations. That's stuff that will actually be handled in the new framework by our friends in the jet group and in the track group as well for the service.
Steve,
So yeah.
Is your vertex finding trigger, it's not a level 1, it's sort of...
Not a level 1. Yeah, we have no track information at level 1.
And does that cause any dead time where you have a large enough buffer effects?
Yes. So yeah, we have to be very selective about where we run tracking, and what we allow to be called a track for the purposes of then doing vertexing and things like that. So we have narrow windows in Z in the impact parameter relative to the primary vertex and other things like that. Our goal is to balance fidelity with what the offline tagger would have versus speed. Yeah, and that was a constant year-by-year challenge in Run 2. We had a massive campaign of CPU optimization that went on for over a year and a half. We even at one point thought about, there's a transition radiation tracker, and we thought about throwing those tracks out and just using the silicon-based tracks. We never had to do that, but we came close to doing it. Right? So, yeah. Okay, and this is just to show you the stability of this algorithm in the online relative to its offline counterpart. So if I look at proton-proton collisions with, as a function of the mean number of proton-proton interactions per crossing, this is the efficiency of the online algorithm for a given operating point, which is usually defined based on how efficient it is at selecting B-jets, true B-jets, relative to its offline counterpart. So for instance, the offline B-tagging efficiency used here was 70%. So if we look at the magenta squares, that's there. That's the 70% online working point, which is the exact partner of the offline working point. And you can see we're up in the high, like 96, 97% relative efficiency to our offline algorithm, all the way up to about 71 or so proton-proton interactions per crossing. We ran out of data there. Okay, so we just don't have any data to make that measurement.
What's the mistake rate?
Depends on the operating point, but typically for an efficiency of 70%, it's under the best conditions, it's about, we have a light jet rejection factor of 300. So 1 divided by 300 would be the mistaken rate.
So light, the jet also includes C?
No, so for C-jets, the rejection factor is more like 8. So 1 in 8 C-jets would be misidentified. Okay.
And when you get higher luminosity, like that's a more...
Right, this could go up to
crossing.
200
Right,
eventually,
so
yes.
like, do you need a hardware, do you need like at the detector level, or is it more computing that would let you...
Come back and ask me that at the end. That's a great question, and we face some recent challenges in that. But that's a conversation, I think, for Q&A at the end. Yeah, I like that question, though. So, all right, let me skip over that. I don't want to leave our grad students on the floor, but we had grad students doing lots of things at SMU. So Maddie here is working on precision measurements of the Higgs using Higgs to ZZ to 4 lepton. All of these students here are students that have worked directly with me, so Jeff, Matthew, and Pei Long. Jeff worked on the 2015-2016 campaign to search for Higgs to BB bar. Pei Long is working on the final Run 2 publication for Higgs to BB bar, improving background modeling and ways of rejecting backgrounds. And Matthew got his PhD over the summer on highly boosted Higgs to BB bar. Jeff's now a Google brain. Matthew's a postdoc on Atlas at University of Illinois Urbana-Champaign. Pei Long and Maddie will defend their theses this year. This is my youngest PhD student right here, Chris Milkey. This was the only photo that anyone had with him in it at this test beam that he did at the DESI laboratory for a chip design that he's working on with our colleagues at the SLAC National Accelerator Lab. He's there on a DOE Graduate Research Fellowship. He swears he was working, although in the picture he's got his feet up and he's got his hands behind his head. But I think he's dreaming about the thing he wants to be working on in this, which is vector boson fusion production of the Higgs and Higgs to BB bar. I'll come back to that in a little bit. So, this is just some of the things that our students are working on in this. All right, so let me get into the measurements that I wanted to show you today, and then I'll have a quick close off at the end. All right, so let me give you a quick hitchhiker's tour of the Higgs boson told through the lens of Higgs to BB bar. All right, so no talk on the LHC would be complete without some baseball card level statistics on producing the Higgs. So the prominent way that we produce the Higgs at the LHC is that gluon fusion process I mentioned before. At 13 TeV, that represents 87% of our production of single Higgs bosons. Coming in at just 7% of production is this next, the sub-leading channel, which is vector boson fusion. Here, quarks present in the protons will exchange vector bosons that fuse into the Higgs. This is just a lower rate process at the LHC. The third most abundant is the vector boson-associated production, where you have direct QQ bar annihilation into a Z, for instance, and then the Z radiates a Higgs. This is also known as Higgs straw lung in reference to Brem's straw lung. And then the fourth biggest process, representing 2% of production, is the Higgs produced in association with either a pair of top quarks or a pair of bottom quarks. We've never observed directly the pair of top quarks, although that's expected to be bigger than the pair of top quarks final state. It's just much harder to observe. T-bar Higgs has been definitively observed by Alice and CMS. And then finally, we have this interesting two Higgs production. So these are all single Higgs production, but what if you wanted to make two simultaneously in a proton-proton collision? This is interesting because it involves at least one diagram where the Higgs, a virtual Higgs, decays into a Higgs and a Higgs on their mass shells. So this right here probes the trilinear Higgs coupling that we're so interested in as a more direct measure of the electroweak potential. The problem with this is that it's competed with by a box diagram that nowhere involves the trilinear Higgs coupling. These actually interfere destructively in the standard model, and so the overall rate of this is suppressed by the interference process, which makes this a bit frustrating. This process comes in at current theory predictions at 0.06% of production of Higgs bosons. So that's a really small rate. We're talking tens of femtobarns in cross-section here versus tens of picobarns in cross-section for gluon fusion. This is about picobarn. Okay, so I'm going to be focused for the rest of the presentation on the vector boson-associated production here for discovery of Higgs to BB. The gluon fusion production mechanism for trying to probe Higgs production at very high momentum, and then finally the di-Higgs production mechanism for probing Higgs self-coupling, at least in the future, if we can observe this. All right, so let me talk first about finding the tallest mountain in sort of the Higgs hunting guide here, and that is the Higgs to BB bar process, which is supposed to be 60% of the branching fraction of the Higgs. All right, so this gives you the sense of the problem, that why this wasn't a discovery channel for the LHC. If you just think of the Higgs going to BB bar as looking for a dijet mass bump, which is ultimately what this problem boils down to, this is, in decades, the cross-section for producing things at the LHC, okay, at various center of mass energies, including 13 TeV. This is in picobarns. These are categories of processes here. So this is, for instance, the proton-proton inelastic cross-section comes in at 10 to the 11 picobarn. The dijet cross-section comes in around 10 to the 6, 10 to the 7 picobarn, something in that range. Single Higgs production comes in at about 55 picobarn, okay? So we're talking about 6 orders of magnitude here, roughly, between dijet production and single Higgs production. Then 60% of single Higgs production will give you 2 jets. This is the tallest mountain. This is the mountain we actually care about. And this is like Olympus Mons on Mars versus Everest on the Earth. I mean, this mountain looks big on Earth, but in the course of looking at other mountains in the solar system, and that would be this dijet cross-section, which we're working against in the LHC, this is not a very big mountain we're looking for. It's a molehill compared to this thing. Okay? So you're not just going to go out and look for 2 jets and then make a mass bump with this. I mean, you can try that game, but that's not necessarily the gold-plated way of seeing Higgs to BB bar. So what we do instead is we trade off rate for cleanliness. And we focused on the vector boson-associated production of the Higgs. So this is Higgs produced along with a Z or a W. The Z or W will decay into very easily identified things, like a charged lepton, a pair of charged leptons, a neutrino. These are all readily distinguished in the LHC and rare for QCD stuff to produce, at least at high momentum. And then you could look for Higgs to 2 jets in that same event where you sort of tagged the event with the presence of an electroweak boson, a Z or a W. All right, so this is what one of those candidate events might look like. This is very cleaned up. Oh yeah, a lot of the pileup has been removed already from the event display. This is not how this would look if you just plotted all the raw stuff in an event like this. There is an underlying event, but mostly these are higher momentum tracks that made it into the event display. We have the dijets here. These are the sprays of particle. You can see the sort of the cones of tracks here leading into large energy deposits in the green electromagnetic and yellow hadronic calorimeter. These are classic hadron jets. And if one could zoom in here, you would also see evidence of displaced production of particles within the context of those jet cones. Over here we have an electron candidate, a single high momentum track, well isolated from other things in the event. Big deposit of electromagnetic energy, almost nothing in the hadronic calorimeter associated with it. Classic electron signature. And if you sum up the transverse momentum of all the objects in this event, see if I went back too far, yeah, there we go, then you'll find that there's something missing, and that's what's indicated by the dotted line. This is the missing transverse momentum. So taking together this dotted line of missing transverse momentum and this electron make an excellent W candidate, W to E nu. All right, so W to E nu, Higgs to BB bar. This is a candidate event. We don't know for sure that this is a Higgs and W event. It's an excellent candidate event for this process. It made it through all of our selections in 2016. Now, the way we do this, we actually have two analyses. The leading analysis uses a multivariate approach. The cross-check analysis does something that's a bit more human-friendly, and that is makes an invariant mass and then fits it. All right? So the less human-friendly approach is that we take all of our variables, and we have a whole bunch of them. Most of these have to do with the kinematics of the B quarks, the kinematics of the lepton or missing energy relationships between these objects in the event. We feed all of this information into a boosted decision tree. A boosted decision tree is just an organized tree of sequential cuts that is optimized by minimizing a function. In this case, it's the error of classification is minimized, and you do that over and over and over again by gradient descent methods, gradient boosting as it's called. You take the hardest to classify events after each round of training, you grow another tree, and you try to improve your classification of the harder to classify events. And you grow a bunch of trees, and then you do a weighted vote of the output. And then you have to map the output onto something human readable. So we map the output so that the most signal-like events tend to accumulate toward 1, and the most background-like events tend to accumulate toward -1. And that's exactly what you see here. So this is black data points. The colored solid histograms are various backgrounds. I'll comment on a few of them in a moment. The red histogram here with no filling, that's what the signal should look like. Now note this is a logarithmic plot. So this actually peaks in a linear scale, but it looks flattened out in a log scale because of the way that that represents the information. So this is a big peak down by -1, very background-like. And this here would be a big peak toward +1, very signal-like. Now you can see here that there's a lot of background. This is the WH search channel for Higgs to BB bar with W to either electron and neutrino, or muon and neutrino. There's a huge background to this from top pair production, that's in yellow. Single top production, that's in darker yellow. And W plus jets, which can easily fake a W boson and a pair of jets that are misidentified as bottom quarks. Not, as was pointed out earlier, these B quark identifying algorithms are not perfect. 1 in every 300 light jets they'll misidentify, 1 in every 8 charm jets they'll misidentify. Okay? Now, nonetheless, even despite that, there's clear evidence of a tension between the data points in black and the top of the sum of the backgrounds, which is the top of the yellow histogram. There's a gap, and that gap is nicely filled by a signal hypothesis whose shape matches this, but fitted to the data with the backgrounds and signal free to float within constraints in this. And at the end of the day, when we fit the model to the data, we see very good agreement between the total model and the data we have in this channel. And it's evidence for a signal contribution to this that's about 1 or so times the standard model expectation. So consistent with the standard model expectation. This is one of only 3 channels that we use. We combine those 3 channels together. This is what the combined plot for the boosted decision tree output looks like. The background has been subtracted off the bottom here, and you can see a very clear contribution of signal. This is significant at about the 4.8 standard deviation level, including systematic errors. So almost a discovery on its own, but when combined with other channels sensitive to H to BB bar, it was a discovery over 5 standard deviations, including systematics. This is a special way of representing the information. It's binned by the sensitivity of the output bin in the boosted decision tree. So the most sensitive bins, the ones most likely to show signal, have a good signal to background ratio are up here. The ones least likely to show that are down here. So this is just a way of organizing that information. This is a bit more human-friendly. So we have in parallel an independent analysis that uses the invariant mass of the digest system. There's very clear evidence that we can reconstruct ZZ and ZW. That's the gray shown here. So that's our control, that's our standard candle in the standard model, is looking for diboson production without the Higgs, and we see that at about 1 times the standard model rate. So that's a good control that this analysis is not creating a signal where none exists. And then there's this shoulder that sits off to the right. That's the because of the resolution of jet reconstruction, the Higgs and the Z peak overlay on each other and get tangled up. So you do have to still fit this distribution to get the contribution from the Higgs, but it's there. It's a little less significant than the boosted decision tree analysis, but nonetheless confirms the observation at about the 4.5 sigma level or so. So this is a very satisfying thing. Of course, people like to see resonances, and there it is. Okay, and so looking across the three channels so far, combining the three channels into the WH and ZH production mechanisms, we see something that when combined all together is very consistent with the standard model prediction for the rate at which this should happen. This mu thing is just that you take the observed rate of a process and you divide by the standard model prediction for the rate of the process. If the standard model is the correct description of nature, you get 1 out of this. And this is very consistent with 1. The standard model explains what we see in the data very well here. And as I said, this is about a 5 sigma discovery, including systematics, and this is using only half the data. So this is from 2018. It only uses half the data we took in run 2, and work is ongoing now to include all of the 140 or so inverse femtobarns of data. But we face a challenge, and that is, and you can see it in these numbers here, this is a good example here, the systematic errors are slightly larger than the statistical ones. This is already a systematics dominated or almost dominated analysis. We can still improve a little bit by adding more data, but we can't only improve by adding more data. So the systematic error comes in at around 0.203 on a mu of 1, all right? And you can see that slightly beats out the statistical error, so versus 0.16. What are the biggest culprits? Well, B-tagging, our calibration of B-jets and charm jets. That suffers from incomplete statistics. More statistics, more, for instance, top pair events used to build a calibration sample will improve that. So we expect that systematic to improve, generally speaking, with statistics. That's one of our few statistically driven systematics. One that isn't driven by statistics but is driven by theory is the modeling of the signal itself. That has about a 9% uncertainty associated with it. It's actually bigger than our largest experimental uncertainty. So while that isn't really where we can make improvements, it's just a call to the theory community to keep pushing on this like you've been pushing on this to improve our understanding of these processes, radiation, hadronization, all the difficult stuff that we have to do some pretty crazy things to get systematics on, picking between two models that we don't know either of which is correct and calling that a systematic. We don't like to do that, but we're sort of stuck there. Modeling backgrounds is a problem, so Z plus jets, W plus jets, and top pair, those are some of the ones I showed you before. They come in with errors at the level of about 6%. And again, because we have to take a lot of these from Monte Carlo simulation, we're slave to theory uncertainties in these that we can't per se reduce, unless we can find better control regions for these things. And then finally, jets. So Atlas is finally adopting particle flow jets as the recommended way to reconstruct jets. And we expect these systematics to improve a little bit, but not drastically. So the biggest improvements we're hoping for will come from B-tagging and our understanding of background modeling. We're not sure we can improve signal modeling or the jet systematics. Those may be somewhat fixed in stone for the time being. Okay, so once you've discovered Higgs to be B-bar, you should use it for something. So one of the things one of my PhD students did was to initiate an analysis that had been done on CMS in 2017 on Atlas. So this is taking the VH that I just showed you and looking at the production as a function of the transverse momentum of the vector boson, either the W or the Z. And you can see here we're probing, typically, we run out of statistics by the time we get to about 250 to 450 GeV in this. This is looking at the cross-section times branching fraction for a bin between 75 and 150 GeV in transverse momentum, 150 and 250 and above 250, adding all that together. And you're down to very few events at that point. The statistical error on this is huge and dominates in that bin. So what you really like to do is continue to push the standard model and go even higher into its theory space by going to very high production momentum where the cross-section is very low, but also the backgrounds get very low, and see whether or not there are any surprises there. Maybe the theory isn't calculating the rate of production as accurately as it could be. And this is one of the things that we were interested in, inspired by an analysis of this on the CMS experiment. So the idea here is that you look at the gluon fusion production of the Higgs, but where one of the gluons in the initial state has radiated a gluon, which then gives a high transverse momentum kick to the Higgs when it's produced. And this can be in excess of 400 GeV in transverse momentum.